afternoon. Spring is here now, nice weather, and we're in the final sprint of the course. We have 3 lectures left. So today we're going to finish the topic that we started last week, which is diversity. And time permitting, we'll get a little bit into coding, which is the last major topic we're going to cover. Then we'll spend all of next week on coding, and possibly a bit of the week after, we'll see. And then whatever time is left, we'll use to touch on some multi-user issues, and that'll be it. Okay, so let's review what we saw last week on diversity, and then we'll just take it from there. So diversity, I told you, is one of the most common mechanisms to mitigate the effects of fading. And it can be used to tackle both shadow fading and multipath fading, although the techniques are different. So the key idea in fading is to send and or receive the data over several routes that undergo hopefully independent fading. So it's as I told you, at an intuitive level, what you want to do is you want to hedge your bets. So the hope is that when you have multiple routes for the data, at least one of them will be received in good conditions. So even if some of them are in bad conditions, at least one of them will be good enough to allow for the data to be decoded. So that's the key idea. The more routes, of course, the better chances, but that comes at a cost. For example, a prime form of diversity is antenna diversity. And here we have some pictures of actual devices that use double antenna reception in this case. And of course, you can always add more antennas, except that it increases the cost of the device and the complexity. So there's a certain trade-off as to how many antennas you would want to use, for example. So we'll get into that today. So there are 2 levels of diversity. One is microscopic diversity, which is designed to fight shadow fading, which is slow fading, remember, that occurs over large-scale distances. And the other one is microscopic fading, which is designed to combat multipath fading over very small distances. Okay, that's the main idea. And the key difference is really in the scale. The techniques are very similar except for the scale. So for microscopic diversity, you need antennas that are very far apart, on the order of sufficiently far that they can have different shadow fades, or sufficiently independent shadow fades. So that can mean tens of meters apart at least, or even kilometers. So that's usually used by playing with the antennas at different base stations. And that is done, in fact. That's microscopic diversity. Our focus is going to be only on microscopic diversity, which is the one that mitigates multipath fading. And a lot of the ideas will only carry over to microscopic as well, but we'll focus, to be specific, on microscopic. And there are essentially 5 forms of microscopic diversity. There are 3 of them, the ones indicated with a star, that involve the use of antennas. So one is space, where you just use antennas that are spaced out. The other one is polarization, where we use antennas that have different polarizations, for example, typically orthogonal. The third one is angle diversity, where you use antennas that are pointing in different directions. And then on top of that, you can use frequency diversity and time diversity. And most wireless systems use both time and frequency diversity and some form of antenna diversity, one of those. So it's a combination. Okay, so let's cover them quickly. Space diversity involves the use of spaced out multiple antennas at the transmitter and or at the receiver. For maximum diversity, we want to make sure that the fading isn't correlated at the antenna, so it's independent. And this requires some minimum spacing between the antennas. So if we go back to our analysis of the multipath fading for the very simple Clark-Jakes uniform scattering model, where the energy comes from all directions with the same strength, recall that we found that the first zero of the autocorrelation occurred at the distance of about 0.4 wavelengths. So for example, at 2 gigahertz, the wavelength is, I believe, 6 centimeters. So that would be about 4 centimeters. Actually, it would be like 2.5. So it's a few centimeters, essentially. That's for the uniform scattering environment. If the scattering is directional, so most of the energy comes from a set of directions as opposed to from all directions, then these spacings tend to go larger a little bit, maybe twice as much, but they always remain on the order of one wavelength. So on the order of a few centimeters at 1 or 2 gigahertz. That's space diversity. Then polarization diversity entails the use of antennas that have different polarizations. And the reason we can use these is because the multipath fading uncorrelates the fading on the orthogonal dimensions. So even if we send a signal on just one polarization, for example, we send on vertical, right? We're going to receive on both vertical and horizontal because of the scattering. And not only that, we're going to receive about the same power on each, and these two signals are going to be uncorrelated. So that's what we exploit here. Okay, and the advantage is that we can get more compact devices because we can put the antennas exactly on top of each other, just cross-polarized. But the drawback is that we only have a few polarizations. So we quickly saturate the amount of antennas that we can have. Angle diversity involves antennas that point in different directions. So the idea is that each of the antennas is going to capture a different set of multipath components. And if these multipath components have different fading, then each of the antennas is going to pick up a signal that fades independently of the other ones. So we have to be careful not to miss any multipath components, because that would mean that we're missing some of the energy. So one has to design this carefully, but that can be done. So those are the three ways in which we can use antennas for diversity. Then we can also use frequency, whereby we send the information over different frequency bands that are sufficiently far apart that they fade separately. So that means that the frequency bands are at least one coherence bandwidth away. Otherwise, the fading is going to be the same, and we don't get anything. Okay. And then the dual of that in the time domain is time diversity, where we send information at multiple time intervals that are sufficiently far apart that, again, they fade independently, which means that we have to allow at least for one coherence time to go by before we send the second transmission. Otherwise, the fading is going to be, again, the same. Okay, so these are frequency and time are actually exact duals of each other. Okay, questions, comments? All right. So we're going to focus on antenna diversity just to make things specific, but most of the techniques carry over also to frequency and time diversity in a very similar manner. And we're going to break it down in two parts. First, receive diversity, where we're going to use multiple antennas only at the receiver. And then transmit diversity, where we're going to use them only at the transmitter. Okay? And one could also combine both and use both transmit and receive if you wanted to, and you would compound the gains. So we're starting as week by seeing receive diversity. So the idea is to use a combiner. Oops. Combiner such as the one we have in figure 7.1. Okay. So we have capital M antennas, and each one picks up a copy of the same signal, S of t, except multiplied by a different coefficient, which is, let's call it H, and it has an amplitude, R, and a phase theta. So for example, the first antenna picks up the signal S of t times H1, which will be R1 times e to the j theta 1. Okay, that's the low-pass notation for the multipath fading of the first antenna. The signal picked up by the first antenna, and there's a second copy picked up by the second antenna, and so on and so forth. So each branch, each antenna, is multiplied by a coefficient alpha, which is complex, so it has phase and magnitude also. And then we just add up these weighted copies, and that's the output of the combiner, and that's what we use to make our decisions. So that's what we use to do the modulation and the decoding and all that, right? So at each antenna we have a certain SNR sigma, gamma, all right? So gamma 1, gamma 2, gamma 3, etc. So if there was no diversity, this would be the SNR, whatever gamma you have. And by combining them, we get a combined gamma, which we're going to call gamma sigma, which is going to be hopefully better than any of the individual gammas. In fact, it will be. So that's going to reflect our gains from the diversity. Okay, so we saw that a key notion here is to co-phase the antennas, co-phase the signals. So make sure that the phase of each of these alphas exactly cancels out the corresponding phase of the multipath channel on that antenna, so that all the signals get lined up, and they add up in phase. So they add in a constructive manner. Okay, so that's a key idea. And for that, we need to know the thetas, which means that we need a receiver that is coherent, so a receiver that estimates the channel. So that's an essential notion here for most of the techniques. Okay, so alpha I is going to be the phase of the ith multipath channel, theta I, except with a minus sign to cancel it out. So it's exactly the conjugate, e to the minus j theta I, times some amplitude a sub I, which for now we're going to keep general, and then we're going to design. Okay, so theta I equals the phase of the fading on that branch, exactly equals its negative, and alpha, this should be a really, a sub I, depends on the time of combining. Let me fix that. All right. Okay, so as I was saying, in general, this requires coherent reception, so we can adjust the thetas. There is an exception, which is when we use selection, where all the branches are ignored except for one. In that case, we don't need to phase the signal at all because we don't do any combining, we just do selection. So in that case, we can use also differential. So that's the only case where differential modulation can benefit from diversity. So, in a bit more detail, when we add up the sum of these alphas times the fading for the corresponding antenna, is r sub I e to the j theta I times the signal s sub t, we get that the s sub t comes out of the summation because it's common. And then the phase of alpha cancels e to the j theta I, okay, by design. And we're left with the summation of the a sub I times r sub I. Okay, so r is the amplitude of the fading on the ith antenna, and a is the amplitude of the coefficient that we imposed on that antenna. Okay? And an issue here is, which we're going to see now in a little bit. Now, a direct benefit of received diversity is that the average SNR increases. So the average of gamma sigma is going to be the average of one of the antennas, gamma bar, times some number bigger than 1, which is the array gain. So this is always going to be bigger than 1, and so the average SNR is always going to increase thanks to the diversity. So that's the first benefit. And more generally, not only does the average SNR improve, but the whole distribution improves. So the worst cases, for example, improve. And that results in an increase in both the average error probability, PE bar, and on the outage probability, P out. Okay, and remember how we compute these quantities. The average PE is just the integration of PE over the PDF of gamma. Okay, and the outage P out for a certain threshold gamma 0 is just the integration from 0 to gamma 0 of the same PDF. So we've been using these already in previous chapters. And here we'll use it again to see how much things improve when we use diversity. So now, in terms of how we adjust the A sub i's, we're going to study 4 forms of combining. The first is selection. Second is threshold combining. And these two are very similar, actually. They're related. Then there is maximum ratio combining. And finally, we'll see equal gain combining. And in fact, we already saw last week the first of these. So we saw selection combining, which is again here. So the idea in selection combining is to output the signal on the base branch. That's it. So the other ones get discarded, and we just retain the branch that has the highest SNR. Okay? An obvious advantage is that we only need one decoder, one radio, because we're going to just choose one. So we can just grab one radio in the receiver and just connect it to the antenna that we choose, and that's it. In the other techniques, we're going to see that we're going to need multiple radios to demodulate all the signals. Another advantage is that cophasing is not required because we don't add up multiple signals. We only add one, which is the best. And so we don't have to align the phases, and so we can use these also with differential modulation. That's an advantage. Now, let's see if we can quantify the improvements. So to make things simpler, let's consider that each antenna, each branch, experiences independent Rayleigh fading, independent of the other ones, with an SNR gamma I, okay, whose average is gamma I bar. Now recall that if the fading is Rayleigh, the distribution of gamma I is exponential, where gamma I bar is the average, okay? And the outage probability for a certain threshold gamma 0, we saw this a couple of weeks ago, is obtained by integrating this PDF, and it's another exponential. It's 1 minus the exponential of minus gamma 0 divided by the average gamma I bar. Okay, so we saw these already. And this is when you don't have diversity. Now, what do we get when we have selection diversity with M antennas? Well, if we have M antennas and the fadings are independent, we're going to have an outage whenever all of them are in outage, right? Because if just one of them is not in outage, we can choose that one, and we're going to be not in outage, right? So the only way that we're going to be in outage is when all the antennas are at the same time in outage. So what's the probability that that happens? Well, because of the independence of the fading, it's just the product of the probabilities. So we just multiply out for I going from 1 to M, the probability of outage on the ith antenna, which is this 1 minus this exponential, okay? And if we further assume that all the branches have the same average SNR, so that this gamma I bar is equal to gamma bar for all the i's, then this product becomes an exponential function. So we get this e to the minus exponential to the power m, where m is the number of antennas. Okay, so that holds if the fading is independent and it has the same average. Now, what's the average SNR at the output of the combiner? Well, as I said, is the average on one of the antennas times the array gain. And in this case, you can the array gain can be found to equal the summation over all the for I going from 1 to capital M, to the number of antennas, of 1 over I. Okay, and we saw that this array gain results in an increase with the number of antennas that is nonlinear. So the most gain is obtained in terms of array gain, is obtained going from 1 antenna to 2. Then we still get some improvement going to 3, but not so much. Even less going to 4, and then so on and so forth. And when we have a large number of antennas, adding one more just doesn't do much for us in terms of average, in terms of this array gain at least. Now, the fact that the array gain doesn't grow much doesn't mean that the outage probability doesn't improve, because what happens is that the outage probability is not determined by the average. It's determined by the worst cases, right? It's determined by the really bad fades. So even if the average doesn't get much better, the really bad fades do improve a lot. In other words, if you have multiple antennas, if you have M antennas, the chances that all of them are simultaneously in a really bad fade are very small. So the improvements are going to be much better in terms of outage than in terms of averages. And in fact, that's the case, right? We can here we have an example. Say we have BPSK. So BPSK needs 7 dB to achieve 10 to the minus 3 error probability. Okay. Now, in Rayleigh fading without diversity, we need to have an average of with Rayleigh fading and with an average of 15 dB, we have that 50% of the time we have outages. So 15% of the time, the instantaneous gamma is going to fall under 7 dB. So that's pretty high. Now, say we go to 2 antennas with selection. So we select the best out of 2. Now, all of a sudden, and each one has still 15 dB average, right? All of a sudden, the probability of outage, the probability that the worst of the 2 falls under 7 dB, drops from 15% to 2%, which is a very good improvement, right? We go from 15% to 2% just by choosing the best out of 2 antennas. We add a third antenna, and that falls to below 1%, so it's 3 in 1,000. So these are dramatic improvements, really. Now, at the same time, the average SNR grew only modestly. So it grew by 1.76 dB when we added the second antenna, and it grew to 2.63 when we added the third antenna. So be careful not to be misled by the fact that the averages increase very slowly, because the outages do get better much more quickly. Okay, now what about the average error probability? Well, unfortunately, there are no closed form expressions for the average PE with selection diversity, even for BPSK. So, let alone for more complicated modulations. So all we can do is just use plots that people have generated using simulations. Okay, so there's not much hope here to do anything analytical. Now, for differential BPSK, it's the only case where we have some meaningful expression. So we have this expression here, which is, not that simple, but it's still manageable. And we can use this to see how the average error probability improves with diversity. Okay. In fact, we can probably look at this formula carefully. So say we have 1 antenna only, right? What does that give us? We have 1 over 2, right? And that's the summation, just what has the first term. Yeah, so I'm doing m equal 1 so far, right? So everything goes away. I think I get 1 plus gamma bar. Yeah, in fact, I have to get this because we had this formula 2 weeks ago, if you remember, for differential BPSK in rarely fading without diversity. So that's the case without diversity. It's a special case for m equal 1. Now, say I go to m equal 2, I get, okay, the 1/2 disappears because now it's 2 over 2. So I get 1 over 1 plus gamma bar. And now I get a minus 1 over, and then I get 1 plus 1, 2 plus gamma bar. And then I get 1 over 1, which is 1. Okay, so that's it. So we get this. And we can simplify this. Let me see. This is 2 plus gamma bar minus 1 plus gamma bar divided by 1 plus gamma bar times. And this, we get everything cancels out. Okay, so if I didn't make any mistakes, I think that's what comes out. It's 1 over 1 plus gamma bar times 2 plus gamma bar for 2 antennas, right? Okay, so now let's look at the numerical example. Let's say that gamma bar is 10. For example, 10 dB SNR per antenna. So with only 1 antenna, right, we get 1 over, this is 11 times 2, 1 over 22, right? And somebody has a calculator, this should be 5% is 1 over 20. I don't know, something like this. I don't know if somebody has a calculator, you can check it for me. It should be in that range. That's for 1 antenna. Now for 2 antennas, we had 1 over 11 times, right, times 12. And here I need somebody to work it out for me, but it's clearly, yeah, 1006. Okay, so we got from 4.5% to 0.7%, right? So I would say, can you divide these numbers? I would say it's about a factor of 6 improvement, roughly. Something on that order. 6, okay. So we reduced the average error probability by 6 by adding the second antenna. So it's not bad, right? You just add the second antenna, you choose always the best of the two. And if the fading is independent, rarely faded, and it's BPSK differential, you improve by a factor of 6 the error probability, average error probability in fast fading. So it's pretty good.
There, the m minus 1 over, that's choosing?
Yeah, that's choose, right? So it's 1 over 1. 1 choose 1 is 1, right? And 0 choose 0 is also 1. Okay, so I think that's where we stopped last week. So now we'll see Erksm combining. And I'm just going to say a couple words here, really. This is a variation of selection combining. which has some interest in terms of implementing it, although it's a little bit inferior. So the idea here is that you scan each of the antennas sequentially, and then you output the first one whose SNR is above some threshold that you've chosen before. Okay? Now, if at some point that antenna that you're tracking, that you're using, falls below that threshold, you switch to another one. And now, if you have more than two, you can actually come up with variations on which one you go to. If you only have two, then you switch to the other one, and that's it. So this is easy to implement for a number of reasons, and it works close to selection, although it's a bit inferior, and I'll tell you why. There's a good picture in the book, which is 7.4. Here it is. Okay, so you can see here what happens, right? So this dashed line would be the signal, the gamma as a function of time on one antenna. And this other line with the thicker dashes would be the other antenna. And you can see that, they're pretty much independent. One is up, the other one is down. That's the idea, right? What you do with Erksm combining, you always try to write the envelope of the tool above some threshold that you've chosen, let's say gamma t. So you start here, and you've chosen the one that was above the threshold. Now, at some point, it fell below this threshold, and you just switch to the other one, right? And you get back on track. Now, here, now this other antenna falls below this gamma t. You switch back to the other one, and so on and so forth. Now, here you have a problem, right? Because you fall below threshold, you switch to the other one, but the other one is even worse off. So here's a proof of why this is worse than selection. So selection would stay with that antenna, and Erksm combining actually is going to jump to the other one, which is worse in this case. So you have these problems in selection, especially if you have few antennas. But other than that, it's pretty similar. And in fact, we're not going to get into details, so I'm just going to leave that as optional material, which means that nobody's going to look at it, but so be it. So much more interesting is maximum ratio combining. So we're going to abandon selection, and we're going to start using all of the antennas at the same time, okay, which is going to be better, and it will be. So maximum ratio combining. We're going to use all the antennas at the same time, and so all the alphas are going to be non-zero, all of them, okay? Now, let's try to optimize these coefficients, these alphas, and in fact, only the amplitudes, because the phases, we know what they are, right? They are the negative of the phases of the corresponding fading. Now, the amplitudes, let's optimize over them. So how do we do that? Well, let's look back again at the combiner, if I can find it again. Here it is. Okay, so what's the SNR at the output of the combiner? Well, let's look at the signals, and then let's look at the noise separately, right? So the signals are going to be, the phases cancel out of the alpha and of the fading. So we get just the A's times the R's times the S, okay? And we add everything up. And that's what we have here. And now we square this, and that's the signal, okay? We just add for all the antennas, the A's times the R's times the S, but I'm not putting the S of t here, okay? But the S of t will, it's not shown, but it's a common term that just comes outside. And we square this, okay? So that's the signal power, signal energy. Now, what's the noise? Well, the noise gets also combined, right? So the noise on the first antenna is multiplied by alpha 1, noise on the second antenna is multiplied by alpha 2, and so on and so forth. So we get we're going to get A1 times the noise in the first antenna plus A2 noise in the second antenna up to M, okay? Now, what's the power of this noise? Well, we have to square this, right, and square this and take an expectation. So what happens is that the noises on the different antennas are going to be independent. So all the cross terms, not only dependent, but also zero mean. So all the cross terms disappear. So we're going to get this A1 squared times the power of this noise, okay, which is n sub 0, plus A2 squared times the power of this noise, which is again n sub 0, plus blah, blah, blah. And then we have all the cross terms, which because of the independence and the fact that there's zero mean, end up being 0. So all you get only are these terms. And so we're left with this. Here it is, the summation of the AI squares times n sub 0. That's gamma sigma. Now, still a function of A sub i's. Now, which are the A sub i's that maximize this ratio, right? So which are the best coefficients so that the SNR after the combining is maximized? Well, it's not easy to do, except for, like for two antennas, you can do it by hand. In general, it's a little more involved, but it can be shown, and it's not that hard actually, that the optimum A sub i's look like this. The optimum A sub I is equal to R sub I divided by the square root of n sub 0. Okay? In fact, you can actually multiply this by some constant. So the important thing is the proportionality. So the key observation that one can make here is that the higher the R, the higher the A, and vice versa. Okay? So the antennas with the higher SNR, so where the fading is better, are weighted more heavily, or have a more important weight on the output of the combiner. And the antennas with the weaker signals, right, are weighted less heavily. So in other words, the combiner is giving more emphasis to the good antennas and less emphasis to the bad antennas, which is kind of intuitive, right? But you can actually show mathematically that this is the optimum way of combining the antennas. And now if you plug these into this equation, well, what do we get? Well, let's work it out. We get in the numerator, we get a summation of A sub I times R sub I. So it's R sub I divided, so we have R sub I squared divided by n0. Or no, sorry, it's square. Okay, so it's the sum of R sub I square, everything square divided by n sub 0. Okay, I hope I didn't make a mistake. That's the numerator. The denominator is a summation of R sub I square times n0 divided by n0. Okay, so the n0s cancel out. So that's it, right? And now we have this summation. You see, this is the same term, except this one is squared, this one is not squared. Okay, so they cancel out. We get the summation of R sub I squared divided by n0, which is what the answer is. Okay, and this can actually be seen to be, you can bring the n0 inside because it's a common term. So you get the summation of I sub R squared divided by n0. And now each of these terms is actually gamma I on the corresponding antenna, essentially. This is the amplitude square of the fading. And remember that the S of t is common everywhere. So at the end we get that the gamma sub sigma is just the sum of the gammas on all the antennas. In other words, the SNR after the combining, which is the sum of the SNRs on each of the antennas that we combine, as long as we optimize the weight in this way. Okay? And that's the best that one can do. You cannot do better than this. You cannot get, in other words, with these antennas and these fadings, with this set of gamma i's, you cannot achieve, no matter how you combine them, you cannot achieve a higher SNR at the output. That is the best. And that's why it's called maximum ratio combining. Now, if all the antennas have the same average SNR, which is usually the case, so what we get is that the average SNR is just the number of antennas times the SNR on one of the antennas. Okay? So this summation, if all of them are equal, just becomes a multiplier. So you have 3 antennas, you triple your average SNR, so on and so forth. So as you can see, this is much better than with summation combining, because here we get a linear improvement with the number of antennas. It's not diminishing anymore, it's constant. And that's the reason that MRC, maximum ratio combining, is the best and the most common form of diversity combining by far. Okay. Now, let's try to quantify the improvements, again, using outages and averages. So, the outage probability, here is a little more involved, right? We can no longer use this notion that, okay, one antenna, the combiner output is not in outage when, or is only in outage when they're all in outage at the same time. Here it's a little more involved, and so you're gonna have to take this result from me. It's in the book. And the derivation is somewhat lengthy, but that's what it comes out to. The outage probability given a FESCOM gamma 0 given by this function. All right? And we have a plot in figure 7.5. Okay, here it is. Okay, so remember this type of plots that we saw already last week. This is the outage probability in logarithmic scale. So this is 10%, 1%, 1 in 1,000, so on and so forth. And this is, in dB, the ratio between the average gamma and gamma 0. Okay, this is the bar is missing here. So this is without diversity for one antenna. This is with 2 antennas, 3, 4. And the way to read this is if you pick an outage level, for example, pick 1%, right? You're on this line, from the 1% line. Imagine a horizontal line here. And so without diversity, you need, if you read out here about 18, that means that your average SNR has to be 18 dB higher than whatever minimum gamma 0 you have, even by your modulation, okay? 18 dB, roughly speaking. Now, say you had a second antenna and you're doing maximum ratio combining. Now you're over here at 1%, and so now you read it down, it's maybe 8 dB. So you gain about 10 dB by adding a second antenna with combining, and so on and so forth. As you add more antennas, you diminish the margin you need. And another way to read it is you pick a vertical line. You pick, I don't know, 10 dB. You say, okay, I'm going to have an average 10 dB higher than gamma 0. So without diversity, I'm going to be at about close to 10% outage, maybe 8%. And with the second antenna, I drop down to under 1%. With the third antenna, I'm down to 1 in 1,000, and so on and so forth. Okay, so you can read these charts horizontally in terms of how much power you save, or vertically in terms of how your error probability diminishes. Yes.
Well, it's not this.
That's all right.
When we choose the operates, we're assuming for, I guess, for the SNR, the gamma, we're assuming that we're going to have, the noise is going to be identical for each antenna.
The same power of noise.
Yeah, the power.
Yeah, so the assumption is that the noise has the same power on all the antennas,
Okay.
but it's independent noise. That's essential. Otherwise, none of this works out, right? So the noise has to be independent and equal power. I mean, you could actually redo this with having different powers at the antennas, and so it can be generalized. But the way I did it here is for this MN0. And sorry, go ahead.
Is that because we're assuming that it's Gaussian noise?
Yes. So the assumption here implicit is that it's thermal noise. So it's Gaussian, but it's also thermal, in the sense that this noise is generated by the receiver itself. So essentially, what we're this noise is the noise that is built by the receiver. So imagine that the signal comes in, completely clean, right? There's no noise on it whatsoever, because there's also environmental noise. But let's assume that there's nothing. It comes completely clean. The electronics generate their own noise, and it's inevitable. It's because of thermal. So the only way to reduce it is by cooling down the receiver. And so very sophisticated receivers actually can be cooled down to reduce them. So the N sub 0 essentially depends on the temperature of the receiver.
fading just on the values?
No, yeah. In fact, that's R. So the R's,
Wow.
right? The R's are the amplitudes of the fading on the antennas, and these are also assumed independent in most of the derivations, right? Does that make sense? Or?
I can assume that the noises are independent of their temperature.
Okay, so yeah, that's a good question. So how come they assume that the noises are independent if they're all temperature related, right? Yeah, so the fact that the temperature related means that the variances are going to be the same. So the temperature, so let me be more precise. The temperature determines the variance of the noise. The noise itself is random. Now the variance of the noise, which is n sub 0, is determined by the temperature. In fact, so this is a very good question. So n sub 0 is actually given by the product of two quantities, K and T. So this is the temperature, and this is Boltzmann's constant. So some of you probably done chemistry courses recently might have this on top of your head. So this is Boltzmann's constant and the temperature in, be careful, in Kelvin degrees. So that'll give you n sub 0. So the n sub 0 that you use in the problem sets, you can actually, if you look them up, you'll see that they correspond usually to K times the temperature of about 290, which is about 17 degrees Celsius. So I'm not very good in Fahrenheit, but like 60, right? So usually n sub 0 that you're using in the problems is just given by Boltzmann's constant, which is 10 to the minus 23 times something, times this temperature, which is the ambient temperature at New York City, June time, or April, I guess. So the temperature determines the variance, but the actual noise is related to an electron motion. So the electrons are moving randomly around. So this is, each antenna has its own electrons, and so nothing to do. Just what's common is the variance. Other questions on this? All right. So let's carry on. Okay, so that's the outage for MRC as a function of the number of antennas and of the gamma 0 that we choose, and of the average of the gamma on each of the antennas. Now, how about the average error probabilities? Well, again, not easy to compute. We have formulas only for one case, which is BPSK. So with BPSK, Brownlee fading, independent on all the antennas, same variance. We have this monstrous formula. So you have to first compute this gamma, which is here, and then you plug it here. It appears in multiple places, okay? And there's a plot in figure 7.6 that's computed using this formula. So it's from involved, but at least it's a formula we can work with. For other modulations, other than BPSK, we don't have anything to work with, unfortunately. But we do have an upper bound. So we can use the familiar approximation, remember, is alpha times the Q function of square root of beta times gamma that we saw. That gives us a family of approximations. So we can parameterize this, choosing the alpha and the beta, depending on the modulation that we choose. So using this approximation, and in fact, approximating also the Q function, which, remember, is very useful, it's very tight, especially at high SNR, with this exponential, we can obtain this bound, okay? So the average PE is bounded by this expression. So it's this alpha is the one that we had here. So remember, there's a table in chapter 6, I believe it was, or maybe chapter 7, one of those two. There's a table where alpha depends on the modulation. So that's the same alpha here, and that's the same beta, okay? So it's a fairly simple formula. And in the case that the fading has the same variance on all the channels, which is usually the case, this product becomes, this multiplication becomes again turned into an exponent. So that's what we get. This is a useful upper bound. It's fairly tight at high SNR, so when gamma bar is large. Now at high SNR, in fact, we can further simplify it because this term here, when gamma bar is very large, this term is much bigger than 1, and so we can just drop this 1 in the front and we get this simplified form. And there's an important observation here, which is the exponent. Okay, so this falls as gamma bar to the minus m. So as we increase gamma bar, the PE bar falls as gamma bar to the minus m. So this is actually a very, this is probably the most common way of measuring diversity, the exponential decay of PE bar with gamma bar. So imagine that I give you imagine I give you a system like a box, right? You don't see anything what's inside. And I'll tell you, this is a receiver with diversity. It has M antennas, and it uses MRC. But I don't tell you how many antennas you have. So try to figure it out, right? Imagine I'll give you an experiment. You can actually, it's an actual box that you can use. So you can measure, you can make measurements of the received signal, and you can measure the error probabilities and all that stuff. So how would you figure out how many antennas you're using? No, you already know the answer. So, sorry, go ahead. Go ahead.
The slope of the curve of the error would be
Yeah, exactly. So what you do is you plot, exactly right. You plot PE bar as a function of gamma bar, and you see what's the exponent. Okay? And in fact, the way that this is done, so this is really how diversity is measured if you don't know what it is. So you plot this, and now how you see the exponent? There's a very easy way, right? So turn this equation into a logarithm. So in other words, take the logarithm on both sides, and you have that the log of the error probability. And what happens when you take a logarithm, right? So the exponent comes down. Okay, so you get the log of alpha minus m times whatever's left, right? The log of whatever's left in the parentheses, which is actually essentially a constant times gamma bar in dB. So essentially you get a plot. What you do is you plot here the logarithm of the error probability as a function of gamma bar in dB. And what you get is a straight line. You get a straight line, and the slope is m. Okay? The slope of this line is actually m. So this constant just tells you where the line is going to be. They just move it up and down, to the left and to the right. But the slope is m. So that's how people measure diversity when they don't know what it is. That's how they measure it. And here we have m antennas. We get the order m, which is the maximum you can get. Okay, so MRC is optimum. It gives us the maximum diversity. All right. So on to the last form of received diversity, which is equal gain combining. Now, the only problem with MRC is that we require that the receiver knows the SNR on each of the branches. Okay, so we need to know. Remember that we need to know. So the coefficients A sub I, each one is equal to the corresponding R sub I divided by the variance of the noise, actually standard deviation. So we need to know the R sub I's. And the R sub I's are essentially, so the R sub I squares essentially are the gammas. So we need to know the gammas. Now, that's not very hard, but sometimes it's interesting to have simple techniques where you don't need to know the gammas. And the simplest technique is equal gain combining. So all you do is you just make all these A's identical. Okay, so you make all these A's equal. So you just make sure that the signals coming into the antennas are phased properly. So you just change the phases to cancel out the phase of the fading so that everything lines up. But you don't touch the amplitudes. You just let the amplitude be whatever it is. That's the equal gain. And we get this expression for the gamma sigma at the output, the combiner. So that's the, so we get this as opposed to this. Okay, so remember that with MRC we get the summation of the gamma i's. Now we're getting this, okay, which is worse, of course. As I told you, the other one was optimum, so this is necessarily suboptimal. Now again, we have problems expressing the outages and the average error probabilities. So in this case, we only have formulas for two antennas, essentially. So the outage probability, we only have the formula for two antennas, and it's already a pretty heavy formula. So that's the formula for the outage probability when you have two antennas. So as a function of the gamma zero threshold that we choose. And you can compare this with the expression for one antenna to see the improvement. But unfortunately, we don't have any formulas for more than 2 antennas. So that's the average. How about the P bar, the average error probability? Well, again, we only have a formula for 2 antennas and for BPSK. That's it. And this is the formula for BPSK with 2 antennas. Now, even though equal gain combining is suboptimum, it is not really much worse than MRC. So typically, it's less than a dB worse. So that's why it's an interesting alternative, because it is simpler and you don't pay much of a price. In fact, let's quantify that with an example. Say we have BPSK with 2 antennas. Each one is rarely faded, and each antenna has 10 dB SNR on its own. Okay? Now, let's assume we do first MRC. So we go back to the formula for MRC. Remember, we had this formula over here for BPSK. So we compute this gamma, and we plug it in here. Okay? So this gamma is the root of 10 divided by 11. And we plug it into the bigger formula, work out the numbers, and what we get is 1.6 times 10 to the minus 3. Okay, so just over 1,000 error probability on average for BPSK. Now, if instead of MRC we use equal gain combining, we plug 10 into this formula over here, and we get 2.07 times 10 to the minus 3. Okay, so we are worse than MRC, but not much worse. I mean, if you look at this, it's about 20% higher, top of my head, maybe a little over 20%, but it is in the same range. So EGC is highly competitive with MRC, and it is quite simpler. So that's what it has in terms of appeal. Okay, so I think this is a good point to break, and after the pause, we'll get into transmit diversity. Okay, so 15 minutes. Oops. Okay, let's restart, guys. So, we've covered receive diversity in the first part of the class, and now we're going to start with transmit diversity. So what's the issue here? Okay, so receive diversity is based on using multiple antennas at the receiver. Okay, so that fits very well on the uplink, which is the link from the terminal up to the base station. So we put the antennas at the receiver, and we're in business. Now, what happens with the downlink? Well, in the downlink, to use receive diversity, we have to put the antennas at the terminal. So that is more problematic, right? Say we want to use, I don't know, 4 antennas, right? We put 4 antennas at the base station, which is something that goes on top of a tower, of top of a building. It's not problematic. You have the room for it. And also the cost is not much of an issue because the base stations are very expensive anyway. They cost upwards of $50,000. So it's not a big deal. Now at the terminal, space is very limited because the terminal is very small and it's very cost sensitive. So installing multiple antennas might be an issue. So how do we serve the downlink in terms of diversity? Well, the answer is transmit diversity, which is to move the antennas to the transmitter. And that's what we're going to talk about now. Transmit diversity is based on using multiple antennas at the transmitter, just one antenna at the receiver. Now, we have a constraint here, which is that the power, even if we add more antennas, the power is going to be the same, right? The power that we have is determined by the battery. We have a battery with output a certain amount of power. And even if we add more antennas, the power is the same. So we have to share it between the antennas. Say we go from 1 to 2 antennas. Now each antenna can use half the power. And if I use 3, you have to divide it by 3 and so on and so forth. Otherwise, you will be sucking up power, quicker, and you try your battery. Plus, the amplifier is designed for a certain power output. So we have to share the power between the antennas. That's the big difference between transmit diversity and receive diversity. In receive diversity, you have a second antenna, it just picks up more power of its own, and that's it. It's no problem here. Here we have to be careful with that. Now, there are 2 approaches to transmit diversity, depending on whether we have or not CSI. So remember when we talked about information theory? CSI was channel state information, okay? The knowledge of the channel fading. So first we'll talk about transmit diversity with CSI, which is very similar to receive diversity. And then we'll talk about transmit diversity without CSI, which is a very different technique. And actually that one that has just been solved very recently. So let's start with the transmit diversity with transmitter CSI. Okay, so the transmitter knows the fading coefficients from each of the antennas to the receiver. So we're going to transmit from each of the antennas a common signal, S of t, times a coefficient, and let's call again the coefficient alpha sub I, which again has an amplitude A sub I and a phase theta sub I. Okay? So remember that in receive diversity, we need to make sure that we align the phases, so we cancel out the phase of the fading with our coefficient, so that the phases are all lined up. So here we want to do the same. Now here we have to do it at the transmitter, so we have to pre-cancel the phase before we send the signal, and then the signal goes to the channel and gets adjusted, gets the phase of the channel, and so the cancellation occurs in the channel, right? So in other words, what we're doing before was, okay, the signal is sent out, it undergoes a phase rotation by the channel, and the receiver undoes the phase rotation, exactly canceling it out, and then combines the signals. Here, what we're going to do is we're going to pre-rotate the phase before it goes, the signal goes into the channel, because we know the fading coefficient, so we know how much the phase is going to be rotated by. So we pre-rotate it in the opposite direction. Then it goes to the channel, it gets rotated back, and the end result is exactly, again, a cancellation of the phases. So it's the same thing, except in different order. So that is how we adjust the phases. Same idea as before. Now, what happens with the amplitudes? Well, we can again use all the techniques we used before, MRC and selection and all that stuff. But we have the constraint of preserving the power. So that means that the sum of the amplitude squares should be equal to 1. Or, if you want, to some other constant. But it has to be equal to some constant. So if we add more antennas, the coefficient on each of the antennas goes down, so that the total sum of the powers has to be preserved. Okay? So the signals go through the air, are added at the receiver, and the phases cancel out, as I told you. We just adjusted the phase so that they cancel out. So again, we get just products of amplitude of the coefficient, amplitude of the channel, times the signal. And this looks exactly what we had for receive diversity. Okay? So nothing has changed, except for the fact that the weighting coefficients have to be normalized so that they meet this condition. That's the only difference. Everything else is the same. For example, say we want to do MRC, right? So again, we just resolve the problem with the constraint of the squares of the A's equaling 1, and we get this modified version of the MRC, where again we have proportionality. Okay, we have that the weight that goes on the ith antenna is proportional to the fading on that antenna, to the amplitude of the fading on that antenna. So the proportionality is the same, but now we have this factor in the denominator that just makes sure that if we square these quantities and add them up, we get 1, right? So if you take this guy and square it up, you can do that. We get Ri squared divided by the sum of the I squared, right? Now, if I sum these quantities, what do I get? If I sum this, right? This is a constant, comes out of the summation, and I get the sum so I get 1, right? So this factor in the denominator just ensures that the sum of the squares is equal to 1. Other than that, we have a proportionality between A and R, which is the key in maximal ratio combining. So again, we have that the SNR at the output equals the sum of the SNRs. And here, I apologize, I forgot the bar. Okay, never mind. So it's the same equation we have for MRC. And so the performance is exactly identical. So outages, outage probabilities, all the formulas we saw for MRC are applicable here too. So by virtue of having CSI at the transmitter, we have transferred the processing from the receiver to the transmitter and obtain an exact dual. So in other words, the performance of a system with M antennas at the transmitter and 1 at the receiver with CSI is the same as 1 antenna at the transmitter and M at the receiver. Okay, so we have just transferred it over in some way. Because we have CSI, we can obtain the same exact performance. And so all the formulas that we derived can be applied here too. Now, this is very challenging to implement because the transmitter needs to track the phases and the amplitudes of the fading on each of the antennas. Okay, so the transmitter needs to track the CSI, and that's very challenging when the user is in motion. So especially the phase. It's very hard to track the phase very accurately when a user is moving around. So at the receiver you can do it, but this is at the transmitter, right? So what you have to do is the receiver has to report back to the transmitter, very quickly, very often, every 1 or 2 milliseconds, have to report back the phase and the amplitude with very little delay. Otherwise, the whole thing falls apart. So it's very hard to implement. So as a result, there was a lot of interest for many years in having transmit diversity that didn't need CSI. And it's a hard problem, and it's much less obvious how to tackle it, since you cannot compensate for the phases as before, in this obvious way and ensure that the signals add up in phase. So you don't know the phase, right? Here we don't know the phase. So how can we adjust the phase? We don't know the phase. We cannot do it, right? So how can we work this out? So for many years, it was thought that there was no way to do diversity without CSI at the transmitter. But they were wrong, so it can be worked out. And here's how you do it. First, let me tell you how not to do it. So imagine you say, okay, I don't know the phase, right? So I have several antennas at the transmitter, one at the receiver, but I don't know the phase between each antenna and the receiver. So since I don't know the phase, I'm just going to send all the signals with the same phase, right? See if I gain something by doing that. So I'm going to send S of t times alpha I from the ith antenna, and alpha I is going to be some amplitude, a sub I, times some phase phi, and phi is going to be the same on all the antennas, because I don't know the phases, I cannot adjust for them, so I'm just going to use some fixed phase for everybody. So does that get me anything? And the answer is no, and we can prove that mathematically, right? So say that also I don't know the amplitudes of the channel, I don't know the R sub i's, so I'm just going to divide the power between the antennas, right? I'm going to say, okay, I'm going to make all the A sub i's equal to 1 over square root of m, so that I square them up and I add them up and I get 1. Okay, so say I have two antennas, I'm going to send half the power on one antenna, half on the other antenna with the same phase phi. Because I don't know the phases, I don't know the amplitudes, so I cannot adjust anything. So I'm just going to send the signals from two antennas or from three antennas with the same phase and the same amplitude and hope for the best, right? And unfortunately, that doesn't buy you anything at all. So what gets combined is this, right? You have, let's go over it. So you have two antennas here, one antenna here. You send signals, which you're going to combine with the receiver. So the first antenna sends 1 over square root of 2 times e to the j phi, which is some fixed phase, times s of t. Okay. The second antenna sends 1 over square root of 2 times e to the j phi times s of t. Same thing. If you square these and add them up, you get 1, so the power is preserved. Phase is the same on both because I don't know the fading. I don't know this. So this is R1 e to the j theta 1, the fading, and here is R2 e to the j theta 2. But the transmitter doesn't know the R's or the thetas. So he's just sending this. And in fact, here you have the formulation for more than two antennas, for capital M antennas. So what you get is that the phi and the square root of m come outside the summation because they're common, right? So in this case, we add this up. And square root of 2 is common, and into the j phi. Right? This is common, so it comes outside. S of t is also common, comes outside. And of course, these, okay, I don't want to confuse you. This is what's sent out. And now the channel is going to multiply these by the fading. So this is times R1 e to the j theta 1, and this is times R2 e to the j theta 2. And that's what's added up. Okay, so the receiver, each one goes to its own fading, and then they combine at the receiver. Okay? So what do we get when we add up these two quantities? So it's a bunch of terms that are common. They come outside. Okay, so the square root of 2 and the phi's come outside, s of t. And then we get the summation of the r's times the thetas, right? Essentially, which is this. Now let's call this r sub I e to the j theta I h sub I. And for example, if this is Rayleigh fading, right, this will be zero mean complex Gaussian, right? So h will be zero mean complex Gaussian, and r will be Rayleigh fading. Now, the sum of complex Gaussian random variables is another complex Gaussian random variable with the same mean, so it's still 0 mean. Now, the variances are going to add up, right? So here I have m h's, so the variance of the sum is going to be m times the variance. So it seems that we're gaining something, right? We have m times the variance, but we have a square root of m here, which exactly compensates for that. So this summation of Gaussian random variables divided by square root of m is a Gaussian random variable with the same variance. So we're back to the beginning. We have the combined signal has a different fading, but with the same variance. So we haven't gained anything. The fading has changed, but it has the same energy and the same distribution and the same mean and everything. So in other words, this approach doesn't buy us anything. Yes?
Isn't it not gain anything, but doesn't it even get worse?
No, it doesn't get worse either.
It can add up, it can add, like if you don't take this formula, but you take the other formula, and like for a case of two antennas, like you could have phi of 0 and 180 degrees and the other one, and they just cancel out.
Yeah, so what happens is the distribution of the sum has the same distribution of each of the components if these are Gaussian. If they're non-Gaussian, it's no longer as obvious. On a particular instance, worsen it, in fact. So if the thetas are such that the signals cancel out, you can get a 0 here. So on a particular point in space or in time, you can get things get worse. In other ones, they're going to get better, right? Sometimes you get lucky, and the phases are actually lined up. So on average, you don't get anything. In some cases, you lose, and on average, you don't get anything. So it's not something approach, right? To just send the signals with the same phase and amplitude. So better way. So it's a very clever way. Oh, it only works for 2 antennas, but and it was devised very recently, 1998, only 8 years ago, by a guy called Angamuti, which was at the time at AT&T Labs here in New Jersey. He's now with Intel, still very active in the field. He's pretty young, and he became famous with this thing. So this is called the Angamuti technique, and it's part of all the third-generation standards now. And you know, the guy was clever enough that he didn't give it any name. So then it was named after him. So that's always a very good idea. If you invent something, don't give it any name, because then they're going to put your name. If you give it a name, it will just be known by that name. This guy was good. He didn't give it a name, so it became the Angamuti technique. And you can find papers and papers talking about Angamuti. So it's a big claim to fame. Now let me tell you how it works. It's a very clever thing. So the idea is very simple. You take groups of 2 symbols. So everything works in groups of 2 symbols. So in the first symbol, so you have groups of 2 symbols and 2 antennas. Okay. Now on the first symbol, antenna 1 sends a signal S1, and antenna 2 sends a different signal S2. Now on the second symbol, antenna 1 sends minus S2 conjugate, and antenna 1 that was, and antenna 2 sends S1 conjugate. And you're sending 2 symbols, you know, you have this usual power normalization, right? So you have 2 antennas that have to share the power. So you're going to have, again, this 1 over root of 2. Okay, so you have 1 over square root of 2 to make sure that you preserve the power. So there's, I think I don't have in the formulas, but there is a 1 over root of 2 implicitly everywhere, as I had here on the board. So let's write this down. On the first symbol period, as we said, antenna 1 sends the signal S sub 1, antenna 2 sends the signal S sub 2. And S sub 1 goes to a fading H1, which is this one, right? Top fading. Is R1 into the J theta 1. And antenna 2 has a different fading, H2, okay, which is this bottom fading. R2 times into the J theta 2. Okay, so that's on the first symbol period. Now on the second symbol period, we do this, right? Antenna 1 sends S2 conjugate. So this is the same symbol that was sent here by antenna 2. Now we send by antenna 1. Okay? So antenna 1 sends S2 conjugate, and it goes the same with the minus also. And it goes to the same fading, H1. So the assumption here, and this is a key assumption, is that the fading remains the same for the 2 symbols. Okay? So this is essential. Otherwise, it doesn't work. Now, the symbols are very short, right? Symbols are about a microsecond. So fading is always constant for a few microseconds, usually for a few milliseconds. So this is not an issue, but it has to be true. So you get the same fading H1. Now, on the second symbol, antenna 2 sends now S1, which is the one that was sent by antenna 1 before, conjugate. And it gets exposed to the fading H2. And then there is noise 1 on the first symbol and noise 2 on the second symbol. And these are independent noises with the same variance. Okay, so let's assemble everything into vectors. So it's more convenient. So let's assemble the received signals over symbols 1 and 2 into a vector. So we put R1, and actually let's put R2 conjugate. Okay, so we build a vector called R, whose top component is R1, okay, this guy, and the bottom one is R2 conjugate. Okay, so we just conjugate this guy out. And now let's express this out. So let's just put this. These equations into matrix form, and you can verify that this is equivalent to that. Okay, so multiply these two guys, you get H1 is 1 plus H2 is 2, okay, plus noise 1, and then here we get this guy times this guy plus this guy times this guy plus this noise, and you conjugate it out, and you get this equation. Okay, so this is just a matrix representation of this relationship with a conjugation in the second row. Okay, so far so good. Now let's give these guys some names. So we're going to call this matrix H sub A for Angamuti. So this is H Angamuti. This vector of S's, I'm calling it S vector. This is N vector with the wall phase notation for the vectors. And so this whole relationship, this vector R, can be seen to equal Angamuti H times S plus N. Okay. Now notice a key property of this Angamuti matrix, which is the following. If you multiply H Angamuti by its conjugate, transpose conjugate, you get something. Okay, so you get a matrix that has 0 off diagonals. So H Angamuti times H Angamuti transpose conjugate is equal to this. H1 magnitude square plus H2 magnitude square, 0, 0. Okay, so you can verify this easily, right? You multiply out this row by this row, and you get 0, and vice versa. Okay, so you can verify this on your own. And why is this always true? Well, this is a consequence of this, really. So the fact that you send symbol 1 and symbol 2, and then you send symbol 2 conjugate, minus symbol 2 conjugate, and then symbol 1 conjugate, the structure on the symbols gives you this structure in the matrix, which has this property. So, as long as you preserve the structure, this conjugation and these sign alternations, this is always true, and so this is always true. So the fact that this matrix is diagonal, yeah, it's actually identical, is a consequence of the structure that Angamuti came up with. So this is the idea, right? So in fact, he patented this stuff. So, with this clever arrangement of conjugations and sign alternations, you get this property. And now why is this useful? Well, because with this property, the receiver can actually discriminate both signals, even though they're combined. So what you do is the following. You take the vector R that we built here. Okay, remember this vector R is obtained by stacking the signal received on the first symbol time and the signal received on the second symbol time conjugated. Okay, so you just receive this, then you receive these on the second interval, you conjugate the second, and you build a vector with these two samples. And this, if you pre-multiply this vector R by H Angamuti conjugate, what you get is a vector Z, which looks like this, right? So you take this R, and you pre-multiply it by H Angamuti conjugate. Okay, so you multiply here. Because of the fact that the Angamuti matrix has this property, what you get, you can do it on your own. You can multiply this vector r, you pre-multiply it by h and a multi-conjugate, and you get this. Okay? So you get a vector whose first component is proportional to the S1, and the second component is proportional to S2, plus some noises and tilde, which are the same noises we had at the beginning, except that with the variance increased by this same factor. So this factor appears everywhere, right? The signals are multiplied by this factor, and the noises are multiplied by this factor. So, what have we gained? Anybody? Is it obvious that we gained something here? So, try to defocus from the math. So what are we trying to achieve here? Diversity, remember? Diversity. Do we have diversity here? So look at this, right? Zeta 1 is equal to this guy times S1, and zeta 2 is equal to this guy times S2.
When your D got MRC, what are the 3 close?
Yeah. In fact, this is we'll get exactly. So I'll get into that in a second. But first, do we have any diversity or not? In other words, the fadings, right? We have this situation, guys. We have two antennas sending out a signal, right? So we're sending these two signals over two symbol intervals with these alternations, okay? And we have two fading coefficients, H1 and H2, which are independent, okay? H1 and H2 are independent. So H1 can be good, H2 can be bad. They're random and independent, okay? This is fading. Now, what we have here is the following. Look, S1 is multiplied by both H1 and H2, and the same S2, right? So what happens if, let's say that H1, let's say that H1 is very bad, okay? Signal from antenna 1 to the receiver is very bad. So horrible, so horrible that, it's like it didn't exist, right? This is so faded that we don't even receive it. So H1, let's say that H1 is about 0, okay? If we had no diversity, we wouldn't pick up any signal, right? Now, are we getting something here or not? Right? So as long as H2 is not bad, we still have H2 here, right? So we're adding, what we got is the addition of H1 squared and H2 squared. So as long as one of the two is okay, we're going to pick up signal. You see? So what Angamuti achieved with this clever transmission technique is to have both signals. Remember, these go out on symbol instance 1 and 2. So it doesn't matter because the factor is the same. What matters is that he got something like this. He got a received signal after all the processing. Let's call it Z. Received signal is equal to H1 squared plus H2 squared times the signal that you sent out, right? So you send out the signal and you receive something that is multiplied by a fading coefficient equivalent that depends on both fading coefficients. So even if one of them is very bad, for example, if the second antenna is completely faded, you still have this guy here that provides signal. You see, so as long as you don't have that both H1 and H2 are dead, you're going to receive some signal. So you're getting diversity here. Okay? So certainly it's much better than we had before when we were sending in this situation. Remember, in this situation, we didn't gain anything. Here we're gaining for sure. Now we have to quantify how much. Yes? Yeah, that is essential. So the H1 and H2 have to be constant for the two symbols, right?
So to send information, you don't have to send it twice.
No, that's a very good point, right? So you send two symbols. So there's a certain repetition, right? But you send from two antennas also. So that exactly compensates, right? In other words, you send two symbols at the same time, S1 and S2, at the same time from two antennas. So it seems you're gaining, right? You send two symbols on one, two symbols on one symbol time. So you see that you gain, but then you repeat on the second symbol time with the conjugation. So you get back to sending one symbol per symbol time, essentially.
But if that was your bit rate, you can only send so many. It takes you twice as long to send.
Yeah, it takes you twice as long because of the repetition, right? But you send twice as much stuff on every symbol because you send from 2 and then S1 and S2. So that exactly compensates. And at the end, the number of bits that are sent is exactly the same, right? Using BPSK, right? Send one bit per transmission, right? So now you send 1 bit from 2 antennas, so you send 2 bits on the first symbol. On the second symbol, you send the 2 bits, except changed, conjugated over and flipped over. So after 2 symbols, you send 2 bits twice. So you send 2 bits. You send one bit per symbol, which is the same that in regular BPSK. So the fact that there is repetition is countered by the fact that you have 2 antennas sending stuff at the same time. So the end rate is not affected. Otherwise, of course, you could do diversity if you penalize the rate. But the key is to do diversity without penalizing the rate. And a multi achieves that. Yes? Yes, that's a very good point. This only works for 2 antennas. And not only cannot be hasn't been generalized, it has been proved that it cannot be generalized. So there are no generalizations, unfortunately. So there are techniques that work pretty well, but none of them is as optimal as this. Like for 4 antennas, you don't have something that is really, really optimal in the same sense. So unfortunately, the answer is no. It's a very unique combination. So what's the SNR that we get after all this? So that, sometimes you get lost in the math and you get lost. What's the SNR that we get? Well, it boils down to gamma 1 plus gamma 2 divided. We can see why that is, right? So on zeta 1, what do we get? Okay, so let me clear the board. So on zeta 1, we get this coefficient times S1. So, right, so we have this guy, sum of the squares, right? And now we have to square this guy to get the power. And remember that there was a factor of 2 normalization that I didn't write, but I had to carry over. Because there are 2 antennas, they have to divide the power. And now, what's the power of the noise? Well, I just told you that the variance of the noise, actually, I showed you here. You see, you had the noise here, was the original noise, okay? So the variance was n sub 0. Now to build, so that was in the vector r. Now to build the vector z, I multiplied r by h on a multi, right? So that increases the variance of the noise, and it makes it exactly this variance. So I have to divide by this guy. Times n0, okay? And this guy cancels this guy, and what I get is this, and essentially this is gamma 1 divided by 2, where these are the gammas on each of the antennas. So we're getting, and remember that for MRC, we're getting that gamma was the sum of the gammas, right? So here we get that gamma is the sum of the gammas divided by 2. So as your colleague was saying correctly, we get almost MRC, except that there's a factor of because of the power sharing. So we get dB. So that's exactly what Angamuti is. Angamuti is exactly MRC minus 2 dB. So that's the only penalty it has. Other than that, it's as good as MRC. So they have no array gain. but it has all the other benefits of MRC. So if you want to compute the outages and all that stuff, you can look at the formulas of MRC and just remember that to divide the power by 2, and the formulas carry over. Okay? So that's the end of diversity. Questions? Yes?
Well, I guess you don't really want to increase your power, but
Well, you can always increase the power, right? But the point is, what else can you do by using antennas besides increasing the power? I mean, increasing the power always helps.
well, I was just talking about like you're cutting, since you're adding another, you're cutting the power in half, but you're probably just having the power enough to have the maximum gain out of those antennas.
Yeah, so you could certainly, if you were able to do an Amuti and double the power, then you would get exactly MRC performance, right? So and you can make a case for that. You can say, okay, an amplifier that can put out a certain amount of power, now I put 2 of them, so I can double the power, right? And that's a valid issue. The concern usually, the reason that people usually normalize the power by 2 is thinking about battery. So these are the transmitter. Power matters in terms of battery life, right? So power, power consumption maps into how many hours your phone is good for. And that's very important. People get very annoyed if the battery discharges very fast. In fact, a big performance metric of a phone is how many hours of talk time it has, how many hours of standby. And power consumption is the big driver of the talk time.
So isn't the 2 antennas, they're going to be at the base station right now, actually?
Right, so it depends, right? If it's at the base, then that argument is weaker because the base is plugged. So then it's about amplifier sizes. So then you can make your point and say, okay, I'm going to add the second antenna with its own amplifier, and so I'm going to double the total power and use an Amuti and get exactly MRC. That's fine. That's a valid point. So in that case, you can just use the formulas of MRC. But just remember that in case you have to explicitly argue that you're actually using the original power now on each of the antennas. So the total power is doubled. But other than that, you're good. Other questions, comments? Okay, so let's go over the summary. Maybe that'll prompt some other questions. So we saw that the main motivation for diversity was to mitigate fading by providing multiple routes for the signal. There are 2 levels of diversity: macroscopic diversity, which is designed to combat shadow fading, and then microscopic diversity, which is designed to combat multipath fading. And it comes in a variety of forms, many of which rely on the use of multipath. So we focused on microscopic diversity, and we broke it down into receive diversity and transmit diversity. A key issue in receive diversity is co-phasing the signals and then weighting them and then adding everything up from M receive antennas. And the benefit of diversity is a more favorable distribution, including an increase in average SNR, which is the array gain. So overall, diversity improves the outage probability, the average error probability, and we've seen some formulas for the cases for which formulas exist. In many cases, we don't have formulas, unfortunately. Then there are multiple ways to do the weighting in terms of amplitudes. So the simplest version is to do the selection. So all the weights are 0 except for 1, which is the best. And a superior form is the combination of MRC, where you weight the best signals with a stronger coefficient and the worst signals with a weaker coefficient. Then we talked about transmit diversity, which is based on pre-phasing the signals before they go into the channel, but the end goal is the same, to get them lined up. And also same weighting. You can use the MRC weighting, equal weighting, selection, etc. And if we have CSI at the transmitter, we can achieve exactly the same performance of MRC. If we don't have CSI, we can use an Amuti with 2 antennas to achieve the same diversity except for the array gain. And if we increase the power by a factor of 2, we get back to MRC performance using an Amuti. So if there are no further questions on diversity, we can close the topic. And we have 25 minutes, so we'll start with a bit of coding. I'm sure you're all excited about this and fired up about coding. It's a very fun topic, a lot of math. So let's cover a little bit of it, and then we'll continue next week. So this is going to put us back. I guess coding is the glue that ties information theory results that we saw before the midterm with all the modulation stuff that we've seen afterwards. Okay, so coding is a little bit the glue there. Coding is an essential ingredient for reliable communication, so we cannot guarantee error-free communication without coding. And so it is a very important ingredient of any digital wireless system. So as long as the rate is below the capacity, we can reduce the error probability as much as we want by using coding, okay, by using better and better codes. So the coding gain is the reduction in DSNR that we need for a given error probability. Okay, so imagine, remember that we found all these formulas when we studied modulations for the error probabilities. For example, BPSK, you have a formula that tells you a given DSNR, if you're using BPSK, what's the error probability, right? So using coding, you can achieve the same error probability with a smaller DSNR. So that would be the coding gain. So modern cellular systems, such as the one that you guys use, feature very powerful coding schemes, very, very powerful. It's a major part of the processing in your cell phones. Coding is a very broad and deep topic, so the book devotes a couple of chapters to coding, one to coding and one to adaptive modulation and coding, which we're not going to see in this course. But there are whole books on coding, many, many books, and there are people who just work on this, full-time research on coding. So it's a very deep topic, it's very broad, and we're just going to scratch the surface here and cover some basic notions. It's very much still a very active field in research. So we're going to start by looking at codes for the unfaded channel with just Gaussian noise. And then we'll see a little bit how to modify the codes in the face of fading. And the main issue with fading is that it causes long string of errors, right? So if you get in a bad fade for a while, that may affect a whole bunch of symbols, consecutive symbols. And so fading has this effect of causing string of errors, which are very problematic for the codes. So there are a number of techniques that address this particular issue. Yes? No capacity, you mean? Of symbols, you mean? Yeah, that's a very good question. So let me repeat. The question is, when we say that the rate should be below capacity, which rate are we talking about, right? That's the question. And that's a very good question. So it's information rate. So it's the number of bits, information bits per second. So, and this is a very important point because there are information bits and there are coded bits, as we'll see now, in this section. And the rate that matters in terms of comparing against capacity is always the information rate, so the true bits. So this is a very good point, and let me revisit it once we've seen what bits are and what coded symbols are. But it's a very, very important point. A lot of people get confused by this in terms of the rate. So let's come back to it once we defined what the bits are. Other questions? Okay, so let's start with a baby example. Parity check. So single bit parity check. This is probably the oldest, simplest, and more essential form of code, the most basic code that exists. And it's based on an additional bit called the parity bit to every block of bits. So say you have a block of k bits, and you're going to add another bit, which is the parity bit, to ensure that the total number of ones is even. And actually, this can be generalized, right? So there are two forms of parity. There is even parity and odd parity. So you can make the number of ones even or odd. So let me just speak even, but the same works for odd, right? So with this very simple technique, we can detect the occurrence of certain errors in the transmission of the block. So say we have this block. We have a block 1, 0, 0, 1, 1, 1, 0, 1. Okay? So we're going to add a parity check. So what do we add? Well, we have 1, 2, 3, 4, 5. We have 5 ones, and we have even parity. So we're going to add a 1, right? So that we have now 6 ones, and we have an even number of ones. Okay? So we were doing odd parity, we would add a 0. We're doing even parity, so we add a 1. And now suppose that we send this block over the channel, and the 5th bit is corrupted. It's flipped in error. So we receive 1, 0, 0, 1, and now 0 here as opposed to 1, and then 1, 0, 1, 1. Okay? The receiver knows that we're using even parity, so it counts, says 1, 2, 3, 4, 5, oops. we have 5 ones, right? This is not right because we're supposed to have an even number of ones. So we know automatically there has been an error. Okay, so it's very simple, but it works. And in fact, the old modems used to use this technique, like 20 years ago. Simple parity bit check. Now, an obvious problem is that if we flip 2 bits, right, it doesn't work. Because if we flip 2 bits, we're going to have 4 ones. So we're going to say, OK, we're good, but we're not good, right? So this simple technique, it's very basic. So it only detects odd number of errors. We have an even number of errors. The error goes undetected. But that means you get the idea, right? We added a bit of redundancy. So we had 8 bits, and we went to 9. So that we pay a small price. We had 1 extra bit. But we can now detect all the occurrences of an odd number of errors. So another weakness of this technique is that we don't know what the error is. Right? So here, for example, if I'm the receiver, I count 5 ones. I say, OK, here at least 1 error, possibly more than 1. But I have no idea what it is. I just know that there's been an error. So we can detect errors, but we cannot correct them. So it's a limited scheme, but it's very simple, and it gives you an idea, right? So the first family of codes we're going to see are linear block codes. And these codes just extend the notion of this single bit parity check. So it extends it to use multiple parity bits. Okay? So using multiple parity bits, we can detect and correct a larger number of error patterns. So we can detect a larger number of patterns of errors, and we can also correct some of them. So we're going to focus exclusively on binary linear block codes. So by binary, I mean that they operate on bits. So we're going to take groups of bits and do the coding on the bits. Okay? Now, you don't have to do it that way. If you're using, for example, QPSK, you could convert the bits. You could take the bits, you group them in groups of 2, map them onto QPSK symbols. So you have 1 minus 1, j minus j. And then you can do coding on the QPSK symbols. But we're going to do that. We're just going to do coding for binary symbols, for bits itself. Okay? Which is actually how things are done in practice. So in theory, you can do non-linear block codes, but usually people only use linear. You can use non-binary codes, but people usually use only binary codes anyway. Even when they use higher order constellations, usually they code on the bits first. So the idea here is to map a group of k bits into a code word of n bits. Okay, so this baby example that we were saying was mapping k bits into k plus 1 bits. Okay, so now we're going to make that more general and say we're going to map k bits into n bits. So we're going to call this an nk binary block code. So the baby example we saw for the single bit parity check is a k plus 1 comma k. Okay, so here we're going to have an n comma k, and n is always bigger than k. So the code rate is going to be defined as k over n, and the data rate is going to be k over n times r sub s, where r sub s is 1 over the symbol time. Okay, so back to your question now. This is the number of symbols per second, and this is the number of information bits per symbol. Okay, so before the redundancy. So multiplying out k over n times r sub s, we get the rate in bits per second. And these are information bits per second. So this is what you have to compare against the capacity. Okay, so as long as this number is normal capacity, you're in business. Okay, so that was a very timely question. Notice that if I count coded symbols per second, it would be a different number, right? Okay, for example, coded symbols per second is just going to be 1 over t sub s, right? So the code rate is always going to reduce that. All right, so we're going to send k bits using n symbols. So I'm going to say symbols to, let me be careful. So we're going to send n bits to represent only k bits. And n is bigger than k. So we have some redundancy. Now, how many values, how many groups of k bits exist? Right? Bits take 2 values, 1 or 0, right? So we get 2 to the k, right? So we have k bits, we have 2 to the k possible blocks of k bits. So we want to send one of 2 to the k possible blocks, and we have code words of duration n bits, right? So how many code words of duration n? So 2 to the n, right? So we have a pool of 2 to the n code words, which are groups of n bits, to send 2 to the k different information blocks, which are the actual groups of bits we want to send. So we have to choose, to construct the code, we have to choose 2 to the k bounded code words from a family or a pool of 2 to the n. That's what we have to do as code designers for this type of codes. We have to design, of all the possible 2 to the n sequences of ones and zeros, we have to choose 2 to the k to be our code words. So how do we do that? Well, first of all, there are some properties that are going to help us, right? For the block code to be linear, and the block code doesn't have to be linear, but there's a lot of nice things that come out of linearity. So we're going to restrict ourselves to linear block codes. So there are 2 key properties that the block code has to be linear. So the first one is that one of the code words must be the all zero. Okay, so that the code word that has all zeros has to be one of the code words. So we have to choose that one. Okay. Now the second property is that the binary sum of 2 code words should always give us another code word. Now be careful here. I've emphasized binary sum. Okay, so let's make sure that we know what we're talking about. So binary sum is this. 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. And 1 plus 1 is equal to 0. Okay? This is binary sum. So it's modulo 2 sum. Okay, so let's see an example. This is a very simple code. Okay, so what's k and what's n here? Anybody for this code? So these are the code words. Anybody? N and k? Okay, what's n first of all? N is the number of symbols of the code word, right? So how many do they have? What's the duration of each code word? Anybody? Is anybody sure?
We have n is equal to 4. And then
No, n is not equal to 4. N is 3, right? N is 3. So each code word has 3 bits, right? So n is 3. Very good. Now what is k here? K is 2. Right? You have 4 code words. So how many bits do you represent with 4 things, right? Log 2 of 4 is 2, right? So how many messages can you send with 4 different code words? You can send 2 bits, right? You can send 4 possible. Okay, with 4 code words, you can send these messages or these blocks of bits, right? 0, 0, 0, 1, 1, 0, 1, 1, right? These are the 4 that you can send, and these are 2 bits, right? So this is a 3,2 code, right? So n is 3 and k is 2. So there are 2 to the k. Remember we said there are 2 to the k code words. So here there are 2 to the 2. Sorry, there are 2 to the k information blocks, right? Which is 4, which are these ones, right? These are the 4 information blocks we can send. And there are 2 to the n code words, right? And potential code words, right? So there are, in theory, 8, and we've chosen 4. Okay, so we had a pool of 8 possible code words. We've chosen 4 of them, which are the ones I chose here. And this build a bounded, and this form a bounded linear block code. Why is it bounded? Because we have the all zeros. Okay, so we satisfy this property, and because the summation of any 2 of them is giving us another one, right? So let's take the first 2. You add these 2 guys up. What do you get? We get the second one, right? So we're good. Now let's add the first and the third. Well, okay, this one is trivial, right? You add zeros with one of the other ones, you get itself, right? So that always works. Now add the second and the third, and you get the fourth. Okay. Add the second and the fourth, right? And you get the third. And add the third and the fourth, and you get the second. Okay, so it satisfies both properties. So this is a valid linear block code with n equal to 3 and k equal to 2. Okay, so I hope this exemplifies the notions. So here I haven't told you how I chose these code words. I just show you that these 4 code words out of the 8 possible ones meet these conditions, right? But I gave them to you. I didn't tell you, I didn't teach you how to show this code, how to pick the code words by yourself. So intuitively, how you want to pick the code words? Well, you want to pick them as far apart from each other as possible. I guess that's intuitive, right? So the farther apart they are, the harder that you make a mistake, right? That you confuse one with another one. So you're going to make an error when you confuse a code word with another one. So to make sure that doesn't happen too often, we're going to put them as far apart as possible. So how do we define the distance between code words? Well, there is a notion that's exactly what we need here, which is the Hamming distance. So this was something that was derived by a guy called Hamming, who again was clever enough not to give it a name, so it became the Hamming distance, who worked at AT&T also in the 60s. So the Hamming distance is just the difference, the number of digits in which they differ. Okay, the number of positions in which they have a different value. So for example, between these two guys, the Hamming distance is just 1, right? 0, 0, 0, and 0, 0, 1. They only differ in 1 bit. Between 0, 0, 0 and 1, 0, 1, Hamming distance is 2. Okay, there are 2 bits that are different, and so on and so forth. So mathematically, you can formulate the distance between the I and the j code words is the summation, and be careful, this is binary summation. Okay, this is binary summation according to these rules of the 2 code words, right? You just add them up binary-wise, and you add over all the digits, and you get the distance, the Hamming distance. So for example, 0, 0, 1, 0, 1 versus 1, 0, 0, 1, 1. Hamming distance is 3. Okay? You add these 2 guys up binary-wise and add over all the digits. And so be careful here, to be precise. This is a binary addition, and this is a regular addition. Okay, so this summation is a normal summation, and this is a binary summation. And some people use a circle around the plus to indicate binary summation, but the book doesn't, so I'm just trying to stay with the notation in the book. So a critical parameter, as we'll see later, for the design of the code, for the performance of the code, is going to be the minimum distance between any 2 code words. Is the min, okay, which is the minimum for all the code words I and j of the distances, right? So you take all the pairs of code words, and you take the 2 that are closest to each other, and that's the minimum distance of the whole code. Now, here is where linearity comes into play. So the fact, as long as the code is linear, we can determine the minimum distance by simply finding the minimum distance between the all 0 code words and any other one. Okay, so for example, in this case, you find that the closest code word to 0, 0, 0 is one of these 2, right? So the distance of this code, d min is equal to 1 automatically. So if you find, once you find the minimum distance between the 0, 0, 0, the all 0 code word and any other code word, that is sure to be the minimum distance of the code. Right? That's a consequence of the fact that the code is linear. So as long as you're meeting these conditions for linearity, this is always true. Okay, so it's a very nice way because it simplifies very much the task of finding the minimum distance. Now there's another notion that we're going to need, which is the weight of a code word. And the weight is simply the number of ones. That's it, right? And notice that that also happens to equal the distance from the all 0 code word. Okay, so the weight of a code word equals its distance from the all zeros. Okay? All right. So we have a bunch of code words, and we have a group of bits we want to send. So how do we map bits into code words? Right? So if I tell you, so imagine that I tell you, okay, I tell you this is my code, right? These are the code words. It's a 3,2 code. Now I want to send, for example, I can send these 4 messages, right? Now say I tell you, okay, I want to send this. I want to send 0, 1 using this code. So I have to pick one of the 4 code words. Which one do I pick? So there has to be a mapping, right? There has to be a way to map groups of bits onto code words. So to do that, you use something called the generator matrix. Okay? So let me see how that works. So the generator matrix for the code is applied to the bits as it follows. You take the bits you want to send, let's call them U. So in this case, this will be U. Right? So U is the block of bits that I want to send. And then I multiply this U by G, which is the generator matrix of the code. And what I get is exactly C, which is the code word. Okay? So this G is the one that allows us to map blocks of bits onto code words. So the G is a matrix that has k rows and n columns. So for this particular code, it'll be a 2 by 3 matrix. Okay? So in general, it's a k by n matrix. Has rank k, and is not unique. So the same code can have multiple G's, and I'll tell you later, why this is so and how you can change G's. Now let's denote the rows of G by G sub L. So G sub 1 with a boldface here. I didn't boldface it. So boldface G, G1 is the first row, and boldface G2 is the second row, and so on and so forth, right? So this multiplication, U times G, can be broken down as follows. The code word is equal to the first bit in the block times the first row, plus the second bit in the block times the second row, plus blah, 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 blah. So you add each of the bits multiplies one of the rows of the matrix G, and that added up gives you the code word C. Yes, this is binary multiplication. You have 1, 0, 1 times 0 is equal to 0, and 1 times 1 is equal to 1, and 0 times 0 is equal to 0. Right? Exactly. Now, codes can be broken down into two classes, systematic and non-systematic. So codes that are systematic have the following property. G looks like this. The first part is the identity matrix. Okay, so just diagonal, ones on the diagonal and zeros everywhere else. And then the rest of G is whatever it is. Let's call it P, right? So that doesn't matter. What matters is that the first part, the first k rows and columns, are equal to the identity. So what's the consequence of that? Well, when you multiply U by a G that looks like this, what you get is that the first k bits of the code word happen to correspond or coincide with the information bits themselves, right? Because this is identical, so they just carry over. So each code word is built by taking first the information bits that you had, that you want to send, and then you add some additional bits, which are denoted by P because these are parity bits. Okay, so the first k digits are the original information bits, and the last n minus k are parity bits, which are obtained as follows. So there are from j, 1 to n minus k. Okay, so there are n minus k columns here. So the first parity bit is obtained by multiplying the first information bit by the first row of P. So P, I'm calling P this part of the matrix, right? So the part that's not the identity. So the first row of P times U1 plus the second row times U2 plus blah, 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 until the kth information bit multiplies the pth, the kth row of P, which is this row over here. Okay, so that's what happens when the code word is systematic. The key is here, right? Systematic codes start, so the code word starts with the information bits themselves, and then the rest are parity bits. If it's not systematic, the information bits don't appear explicitly, so all the bits here are just used by combining the information bits themselves. And any block code can be made systematic by working on G. So if I give you a G, I give you a code and say, okay, this is your G, right? Can you make this systematic for the same code? Yeah, you can actually start, playing with the rows, reordering rows and columns until you get something that looks like this. And what you've done is, the code is the same. So what you've changed is the associations between information bits and code words. So you change the mapping, which is G, but the properties of the code words, the distances, everything is the same, so that you change which bits map onto which code word. Okay? And I think that you guys look very tired, so that's enough for today. Let's stop here and we'll pick it up next week, okay?